Now let's talk about distributed generation, or DG. So here is an overview over typically partakers in today's grid system. And the term distributed generation is used to describe small-scale generation in general, installed near the final consumers typically and operating in parallel to the grid. So due to its size and location, of course, DG sources are typically connected to the distribution network. That means like the low and medium voltage grid. The size of the DG sources varies from, you can see a few hundred watt up to a few megawatts or even a few tens of megawatts. Nevertheless, it remains at least 1 or 2 orders of magnitude smaller than the conventional centralized bulk power plants. Although energy generation technology may qualify as DG, the technologies which are already dominating this field are expected to play an important role in the future are wind turbines, as we know, photovoltaics, and also co-generation of heat and power, and to a smaller extent also small-scale hydroelectric plants. So DG resources encompass electricity storage technology, as well, most important being batteries and flywheels. Hydrogen storage in association with fuel cells or are also expected to play an important role in the near future. And we can say that the grid, once passive and static, as we see here, with a limited number of distributed generators, is now active and much more dynamic in a sense. When we look at the power system analysis, we can have several questions when we start to do such analysis. Which way does the power flow? The active power be and the reactive power. The classic way is you have a generator side and a load side. Today we can have a two-way flow much more, so we can have generator on both sides and vice versa. So what are the voltage levels in the system? That's another question. What about grid losses? And typically we can have customer that complains on voltage challenges that are typically from grid system with what we call low short circuit capacity. We will come back to that. So another question is then, is the connection point strong? When we increase the penetration of power from DG, so what are the benefits or possibilities we have with that? We can increase the renewable energy resources and of course lower CO2 emissions, peak shaving possibilities, reduction or delay in the need for large infrastructure upgrades. We can also reduction in stress on transmission lines, that can be very good. Improved efficiency, of course, reduce losses in distribution system, and of course ancillary service, helping systems to the local distributed systems. And on the other side, what can be the challenges, the obstacles, the disadvantages for this increased penetration of DG? Of course, we can have more voltage rise because of the reverse power flow. That can be one thing. We have the bidirectional power flow caused by DGs and transformers, tap changers, and also the dynamics between them can be a challenge. The power quality in low voltage and medium voltage grid is one challenge. We can have weak correlation also between the residential load and the power production from the DG system. And of course, intermittency, that you have on and off energy production and store. Then we need energy storage in order to ensure safe and reliable operation. We can have others such as regulatory issues, economic feasibility, and of course, market mechanism. Here on the right hand side, you can see a map of all the small-scale hydropower plants around in Norway. A lot of dots around in Norway, so it's very distributed. Typically less than 10 megawatts, and then it has a typical long operational time, can then contribute with voltage control. It can also run as a power factor control. But typically it's that you have connected to a weak distribution grid, and you can have some voltage variation due to that, and may occur with production. So that is large amount in Norway for small-scale hydropower plants. The point of common coupling or connection to the grid of the DG is another interesting topic. An important concept in the DG interconnection is of course the PCC, the point of common coupling, as opposed to the connection point of the DG station. So the PCC is the point of the network nearest to the DG installation, where other network users such as producers or consumers already exist or may be connected to in the future. When an extension of the existing network is necessary for the interconnection of a DG station, it can be, as you can see here in the future, then the PCC is located at the network side end of the extension. So the connection point of the DG station, on the other hand, is the actual point of coupling to the network, which is located at the terminals of the DG station. The significance of the PCC is that the power quality related to technical criteria are mainly evaluated at this node connection, rather than at DG station terminals. So the physical interface between the DG installation and the network is the coupling substation, which includes the energy metering arrangements and the necessary switch and protection gear, typically. And you can see here for typically you can have different structure for low voltage, 1 phase, 3 phase, medium voltage and high voltage. So in the way that you depending on which voltage level you are actually connecting, you need to take certain measures. We will not go into all of these details here, but it's an important topic that you should recognize. And of course, as you can see up on the right, you have the short circuit capacity, the SK, that will be very important when you connect to the point of common coupling. Typically you want to have not so high voltage variation, as you can see in the figure down here on the node voltage. So typically between plus minus 5% of the rated or nominal voltage is something that you are looking at. So when you come to distributed storage, then one question can of course be the short-term or long-term storage. What are you going to use it for? And the primary objectives will be then can be like peak load shaving, and storage of off-peak wind energy, power smoothing for large solar arrays, for example, and ancillary services, as I said before. Black start capabilities, feed reliability improvement is also important things. To the right hand side you can see of course an overview of different energy storage technology, and you have you can see the battery. Typically you have the electrical cars in the leaf, you can see it's pointed out where you have. So depending on how much energy you want to store and the rated power, you choose the right technology. Of course you can have other like hydrogen, typically gas, or pumped hydro storage is also possibilities. To look at one interesting case, I will say, so what is a smart distributed storage solution we can look at? For example, for electrical vehicles, probably Norway is one of the biggest batteries we have access to for a regular customer. So if you look at, for example, the Leaf with 40 kilowatt hours with a lithium ion battery, typically have a range of 270 kilometer, about 1.5 kilowatt hours per 10 kilometer. Let's assume that you have 2 million passengers cars in Norway, where electric driving on average is 15,000 kilometers per year, for example. That equals about 3.5% or 5 terawatt hours of total annual and Norwegian electricity production, actually. So if all cars were charged from empty to maximum charge simultaneously, if you can imagine that, we can see that we have around 80 gigawatt hour needed. And that means 1% of one of our largest hydro storage reservoirs, Blåsjø, of 7.8 terawatt hours. So actually, it's not so much when you look at the storage of water. And in Norway we have a lot of that. So that means we are quite a big battery here in Norway. We have possibilities. So some challenge is of course to organize the system when you have so many small batteries, all switching on and off, and also control systems. One idea is of course what we have, the community energy storage. So you can imagine you have several houses, all fast electrical vehicle charging possibilities. How will you do it? And small amounts of energy storage and the feeders of residential areas. So this has possibility where you go several houses together to have one actual battery, combined with maybe a PV concept, As you can see, here's a case where we have a 25 kilowatt low voltage unit protecting small groups of home. So this is a way you can imagine in the future we can do it. Nearby our university in Skien, we have a stadium that is the Skagerrak Stadium, and we have one case here for a microgrid. Actually, that is very interesting. So they have put down solar panels on the stadium rooftop, as you can see here, and so when they did this, and they're doing research on that now, is of course how it will be for the grid surrounding it. The challenge here is that it is quite strong grid, as you see, less voltage challenges this system, but we can have some kind of high harmonics due to the converters and the switching. So here's how it's constructed. You have then the PV panels on the rooftop, and you have energy storage, a battery, and it can, and then of course you have a connection to transformer station. One way that I wanted to use this is, of course, you have the match day on Sundays. Typically, you have where your stadium is full, but the rest of the week, or mainly, is empty or not so much people in the stadium. So then you can, of course, see that here you have the red one is then the charging of the battery, and the blue is charging of the battery, and you of course can see the consumption in the gray here. So typically in the peak here, you will then take energy from your battery, and after that day you start to charge again. So this is what typically concept of peak shaving they are using this for. In Norway we have a consortium called Sineldi, and it consists of many companies that are going together to look at how can the grid system in the future look like in Norway. So they have smart grid scenarios and transition strategies, and you can see here are some of the mini scenarios they are looking ahead for. And energy storage is important, customer flexibility, power reliability, components, microgrid planning, maintenance, operating the grid, cybersecurity, and distributed generation, and also diesel-TSO interactions. So this is all important topics for this consortium or the research center. Importance is how important is the driving force, is the system innovation in the distribution grid and development towards that. They have made some kind of overview for the driving force, and they're saying that the power electronics, the power intensive loads, and also changing consumption patterns, fast changing power flows is very driving forces. There are some uncertainties, of course, with low uncertainty of development direction of driving force, but this has a high impact and importance. So here's some useful references I use for this introduction lecture, if you want to go more in detail on this.